Hello everyone, this is Coding with Jazz, and today I want to take the first step in creating a theory for the n-by-n Rubik's Cube and find a way to solve it without using any outside sources. And this first step is to solve the 2x2 Rubik's Cube. The story starts with this book I got from the library. I was curious to learn a bit about group theory since it's something I never actually learned about while I was at college. And so, yeah, as I was reading through the book, I wanted to kind of explore some of the ideas by using a 2x2 Rubik's Cube. And the cool thing about the Rubik's Cube is that it's just a massive group. What is a group? So a group is a set of elements along with an operation that we can kind of think of as multiplication, but we'll denote it with the asterisk symbol. So we can use this operation with any two elements in our group, and then we should get something within this group. So that's one property that the group must have, is that if we multiply any two elements, we need to remain within the group. So then another operation that we need is that we need the operation, the asterisk operation, to be associative. So that means that if we have So we can either multiply xi and xj first, or we can first multiply xj and xk and then multiply by xi, and we should get to the same result. And then another property that a group must have is that there should be an identity element. And this identity element must have the property that if we multiply it by some element of our group, then we need to get back that same element. And it should work in either it should work on either side, because we're not necessarily saying that a times b equals b times a. Right, and then we have the fourth property, which is that we have an inverse. So if we can just pick some xi from the group, then there needs to be another element of the group such that we can get to the identity again. So we could say like they're inverses. So how is the 2x2 Rubik's Cube a group? Well, let's take G to be all of the possible ways that you can twist the cube with any number of moves. And so then the multiplication operation is do the first move or series of moves, and then followed by the second move or series of moves. So this is one element of the group, and then this is another element of the group. So if we were to multiply them together, we would get this and then this. So then 2 is a little hard to show on the Rubik's Cube, so we'll skip over it, and maybe we'll come back when we get into the more kind of into the math behind the Rubik's Cube. So now let's go on to number 3. There is an identity element of the group. So that is just the elementary operation, do nothing. Yeah, so if we say do nothing and then do this versus do this and then do nothing, we end up with the same cube. And then finally, number 4, every operation has an inverse. Simply do a series of moves and then do the opposite. And so there we have it. The 2x2 Rubik's Cube is a group. So now that we have this Rubik's Cube numbered, we can try and write down what happens when we make a turn like this, for example. So let's take a look at phase 1. If we do this, then it's going to move to the position where 6 used to be. So we can write down like 1 goes to 6. Okay, so 1 goes to 6, and then what happens to 6? So it looks like 6 is going to go to where 13 used to be. And then if you think 13 will, so 13 should go to where 18 used to be. And then finally 18 goes back to where 1 used to be. So then we can write down the transformations for each of the 8 other faces involved in this turn. And so now the cool thing is that, well, we've just described how a rotation, what the entirety of what this move means. It means 1 goes to 6, 6 goes to 13, 13 goes to 18, and 18 goes back to 1. Additionally, all of these things will happen, and all of these things will happen. And another thing we can see from this notation is that everything kind of will shift over one position to the right each time. So if we were to repeat this operation multiple times, then they'll shift that many kind of spaces to the right. So we can also see that if we do the operation 4 times, then, for example, if we start at 1, we'd go 1. Doing one operation moves us to the position 6. Doing the operation again moves us to position 13. Doing it another time moves us to 18. And then doing it a 4th time moves us back to 1. And so what this is saying is that if we do the operation 4 times, we'll be back, 1 will go back to where it started. And the same thing kind of applies for any face. If we follow the arrow 4 times for any of them, they'll land up back to the same place where they started. And then we can see, if we kind of do this once, twice, 3 times, 4 times, we're back to the same position that we started at. And in group theory, we would call this a cyclic group. So now let's go back and clean up our notation a little bit, so that we can kind of work with it a little bit better. So let's say 1, 6, 13, 18, parenthesis, represents the same thing as 1 goes to 6, 6 goes to 13, 13 goes to 18, and 18 goes back to 1. And so then similarly we can write these 2 operations. And then we can name the turn as W for turning the white face a quarter turn counterclockwise. And then we can do a similar thing to find R, which is turning the red face a quarter turn counterclockwise, and B, which is turning the blue face a quarter turn counterclockwise. However, after using this notation for a little while, I found it kind of cumbersome. With 24 different faces, and it was kind of too hard to see what was happening in an algorithm. It's kind of too hard to kind of add up two moves, and it didn't represent how like the three faces on a corner stick together. And so I came up with a new notation that solved some of these problems, made it a lot simpler, and split up kind of the problem of positioning where the corner is from the problem of kind of orienting the corner to like be in the right orientation. So what I'm gonna say is that we have a cube here, and then we number the cube, and then we can say that the face on top is W, the face kind of on the back right is B for blue, and then the face on the left is O for orange. So if we place our cube like this, we have white on the top, orange on the back left, blue on the back right. So then we can represent white by the permutation just simply 1, 2, 3, 4, and then 4 goes back to 1. And then similarly you can swap over and, well, think of yellow as turning a quarter turn counterclockwise. So we say y equals 5, 6, 7, 8. We can say green equals 1, 4, 5, 8, and so we can look green going counterclockwise to a quarter turn is 1, 4, 5, 8. But we also want a way to kind of describe the orientations of these cubes. We're going to look at the white and the yellow faces, because each corner either has a white face or a yellow face, but not both. And so we look at the white or yellow face of the cube, and we say, how far is that from the white or yellow face that the cube is on? Because a cube can't be on both faces at the same time. So if the white face is on the white side of the cube, then we can say that that corner is at 0, orientation 0. But meanwhile, this cube is now, this kind of corner is not on the white face of the cube, even though it's on kind of the white side of the cube. And so we have to give this a different orientation number. And so we give it an orientation of 1 for being kind of one face counterclockwise of kind of the correct orientation of white face on the white side. And then if we turn it one more time, the white faces are on the yellow side, and this is on the yellow side of the cube. So they are correctly oriented, we'll say, and so that's orientation 0. And then here we have, this is on the white side, and it's kind of 2 spaces counterclockwise of the correct orientation, so that would be an orientation 2. And so now we can fill in what it means to do a green turn with a notation. So what I'll say is that I put an exponent. If the orientation is not 0, we add an exponent to say to the permutation to say what how the orientation changes. So this went from a 0 to a 1. So the orientation changed by 1. So we'll add a little exponent of a 1 there to say, yeah, you can do the permutation. When you do this permutation, move corner 1 to position 4, and also change its orientation by adding 1. And then if we look at 4, it will change orientation by 2, because we go from being on the white face to being 2 counterclockwise from being on the yellow face. And then we look at 5, this is 1 counterclockwise, so that's a +1. And then we look at 8, it moved to 2 counterclockwise of the white face. So that would be our green permutation. And then we can kind of fill in the rest of the permutations in a similar way. And yeah, so now we've kind of condensed our notation to make things a lot easier for us. So now we can use this notation to consider one of the moves that I found to be useful on the 2x2 Rubik's Cube, which is red counterclockwise, so that's an R. Then it is Y Y clockwise, so that's a Y, so I'll say -1 for inverse. And then we go red back, so that's R inverse. And then we can say Y, another turn Y inverse. And then we have G inverse. And then finally, we have Y, because we go like this, and then we have a G, which is going back up. And so the reason I like this move is because, as you can see, it kept these two corners in the same position, but it swapped these two corners. And so it's kind of a useful move for changing positions, but it has the downside that it also changes the corners in a little, kind of in an unpredictable way. So let's see how we can use this notation to kind of figure out what this move is doing exactly. We just kind of expand what it means. Right, so we're inverting Y here. So Y is 5, 6, 7, 8. A simple way to invert a permutation like that is to say, just write it down backwards, because we know that we want, instead of saying 5 goes to 6, 6 goes to 7, 7 goes to 8, we want 8 to go to 7, 7 to go to 6, and 6 to go to 5, and 5 to go to 8. So then, but now, okay, with R inverse, we have to additionally deal with our kind of exponents that are representing the orientations. So let's think about it for a second. We have this move. So when we do R, what are we doing? We're saying 2 goes to 1, and we rotate by adding an orientation value of 1. So the opposite of doing that would be saying 1 goes to 2, and we kind of subtract out that orientation of 1, or we can also say that as we're adding an orientation of 2, because we have basically 0 goes to 1, goes to 2, goes back to 0. So if we start from, so you want the opposite of going 1 plus 1 would be to go plus 2. You can see kind of from that diagram how we're kind of doing the same thing of permuting the orientations in the same way we're permuting the positions, but we've kind of separated the problem into two different problems that are separately a lot easier to solve. Okay, so let's just finish expanding out this equation. Okay, so now we have our expanded out equation, so let's kind of simplify it down to to see what this move does. So we start with 2, and let's say 2. Where does 2 go? Well, 2 rotates by 1. So let's just keep track with like some scratch paper over here. So we have a 1. So we rotate 2 by 1 and we're at 1. And then we go here, there's nothing that changes in this permutation. Then we apply this permutation. Now we're at 1. And so now we apply a rotation of 2. So that means that we're at 0. So this is the orientation, O for orientation, and then P for position. So we went from position 2 to position 1, and we rotated by 1. And now we went from position 1 back to position 2. We rotate by 2. 1 plus 2 gets us to 3, and 3 completes the cycle and brings us back to 0. And so now we're at position 2. So let's write that. And now let's go. We don't see another position 2, so we're back at position 2. Our orientation has not changed, so I want write an exponent. And so we know that 2, under this permutation, 2 is moved back to itself. Now let's look at 1. 1 rotates by 2. Let's reuse our table over here. So 1 rotates by 2 and becomes an 8. Then 8 becomes a 7. So we're at 7, and our orientation doesn't change by that 1. Next we move on to the this permutation. So 7 rotates by 2, becomes an 8. So 8, and so we add 2 to 4, we get we add 2 to 2, we get 4. Then we divide by 3, and we take the remainder after we divide by 3, and we get 1. So now we're at 8, and we go back to 7 again, and we don't change our orientation in that one. And then 7 goes back to 8, orientation unchanged, and then 8 rotates by 2, getting us back to orientation 0 and position 1. So 1 is also unchanged. So now what is this saying? We have 2, 1, and 7 are completely unchanged. So you can see over here on our little diagram, these 3 corners will be unchanged. Then we know 8 and 5 will swap places, right here. And then we know that 8 will be rotated by 1 counterclockwise, and 6 will be rotated by 2 counterclockwise. Now let's try this move again and see if this is what really happens. So we go with R, Y inverse, R inverse, and then Y inverse, G inverse, Y, and then G. So now as we can see, corners 1 and 2 are exactly as they started. And then if you look, we can see that these 2 corners have swapped. They are corners 8 and 5. And so they've both swapped, and we can see that corner 5 that used to be here is now here. And it is in the correct orientation, orientation 0. Meanwhile, corner 8 has gone to position 5, and it has rotated one space counterclockwise with its orientation. And then we look at corner 6. It is in its correct position, but it has rotated two. Its orientation has changed by +2, and it's now the yellow face is over here. Another cool thing about this move is it shows us a cycle in what we're doing. So let's just focus on 8, 1, 5, 6, 2. So we can see if we do that move, this is what happens. If we do this move again, 8 goes to 8 rotates by 1, becomes a 5, and then 5 becomes an 8 again. So we would get 8 rotates by 1. Then we get 5 becomes an 8, and then rotates by 1 and becomes a 5. And then we got 6 rotates by 2, and then rotates by 2 again and becomes a 6. So if we do this twice, everything rotates by 1. So this is one move, this is 2 moves. So if we do this move times 3, then we should get 8 rotates by 1 3 times, which means it should be back to 8. 5 rotates by 1 3 times, meaning it should be back to its original orientation, and 6 rotates by 1 3 times, so it's back to its original orientation. Let's pause here for a second to appreciate that doing the move twice is the move that we're looking for, that only changes the orientation but does not change the position of the corners. So now let's do this move 6 times and see that the cube returns to its original state. As we can see, the cube is back to the solved state. Okay, so now let's see how we can put everything together to solve the 2x2 Rubik's Cube. So we start by solving the white face, which is simple enough. We just move the corners into their positions. Okay, so now we have a solved white face. Let's look at the bottom. And it looks like we have these two corners in their correct positions. So all we have to do is swap these two corners, and then we'll have all of the yellow face corners in their correct positions. So we use our move one time to swap these two corners, and now they're in the correct position, and now all of the corners are in the right position. Now let's write down the orientations of our corners. We have one corner in the correct position, then one at position 1, and then the next one is at position 0, and then the last one is at position at orientation, not position, at orientation 2. And then we can change any 3 corners by adding 1 to their orientation using our move. And our end goal is to get all of the orientations to 0, so we can do this simply by saying we rotate everything except for the corner in orientation 1, and then we rotate the 3 1s, and then we rotate the 3 1s again, and we're at 0. So let's try this out and see if it works. Okay, so this corner is at orientation 1, so we leave it alone, and we put it here to do that, and then we do our move twice. Okay, so now we have orientation 0, and then orientation 1, orientation 1, orientation 1. So we leave our orientation 0 corner alone, and then we do our move twice. Okay, so they've all shifted by 1 orientation. Now we do it twice more. and we have a solved Rubik's Cube. Thanks so much for watching, and if you have any questions or comments, please leave them down below, and subscribe to stay tuned for my next video where I'm going to show you how I solved the 2x2 Megamorphics pyramid Rubik's Cube puzzle.